Welcome to Network Theory. Today we are going to be discussing about the famous Thevenin and Norton's theorems. The references which have been used: Ravish R. Singh, Circuit Theory and Networks; William Haight, Electrical Circuit Analysis; and Charles and Sadiku, Fundamentals of Electric Circuits. Now the contents which we are going to be discussing are as such: Thevenin's and Norton's theorems and examples with independent and dependent sources. Okay. Now what is a Thevenin's theorem? It is a very useful theorem which states that any two terminals of a network can be replaced by an equivalent voltage source VTH and an equivalent series resistance RTH. Now, if you have a complex network like this connected to a load resistance, and you are supposed to find out the current through this particular resistance. So this resistance RL can be anywhere connected in the network. So whatever it is, the network is shown in this form. The Thevenin theorem says that you can replace the complex network at the load terminals by this much part, which is given by a VTH, a source voltage source, which is called as VTH, or the Thevenin's voltage source, in series with the resistance, which is called as a Thevenin's resistance. Now, this whole circuit is connected in series with RL to find out the current through the network, as since it's a series circuit, the current would be VTH divided by RTH plus RL. So this is what the Thevenin's theorem says. Okay. Now, when we speak about the Thevenin's theorem, we have already seen that a complex network can be replaced by this form, where there is a voltage source VTH in series with RTH. Now, this VTH volt, or the Thevenin's voltage, can be found out by finding the voltage across the load terminals with the load replaced by an open circuit. So if this is the original circuit, remove the load, which means you open circuit the load and find out the voltage at this terminals, that is VTH, right? Now, next, when you're finding RTH. So what is RTH? Again, load resistance you remove, that means you open circuit the load resistance. Then remove all the sources in the circuit. So which means that all independent, and that also all independent sources have to be made equal to 0. So note the point that we are speaking about only independent sources. So dependent sources cannot be made 0, as we have seen already. Independent sources can be made 0. So how do you make the sources 0? If it is a voltage source, you can have two types of sources, either independent voltage source or an independent current source. If it's a voltage source, it is replaced by a short circuit. And if it's a current source, it is replaced by an open circuit. So this is a procedure for finding out VTH and RTH, that you first remove the load resistance or open circuit the load resistance, find out the voltage at this terminals, which is given by VTH. Then keeping the load resistance removed or open circuited, make all the sources in the network. Note the point that we are speaking about only independent sources. All the independent sources to be replaced. Voltage sources by short circuit and current sources by open circuit. So once you do that, you find out the equivalent resistance till these terminals. Obviously, this load resistance has been open circuited. So till at the load terminals with the resistance open circuited, find out the equivalent resistance. So this is your RTH. So once we find out VTH and RTH, our circuit is like this. So the complex network has been replaced by this VTH and RTH in series. Now connect back the load resistance and find out the current through the load resistance. Now this is a simple series circuit, and you can find out the current like we have already seen, because it's a series network. So current is going to be equal to VTH divided by RTH plus RL. And this is, the advantage of the Thevenin's theorem is that once you find out VTH and RTH, for any load, you can find out the current. So for this theorem becomes very useful if you have got variable loads in the circuit. So if RL is a variable resistor for different, that means there are different values of RL which can be there in the circuit. You're going to be, the circuit remains the same, the network remains the same. So you can find out VTH and RTH, because anyway you are removing load resistance for finding VTH and RTH. So the advantage is that the same VTH and RTH will hold for any other load resistance, and you can find out the current. VTH divided by RTH plus RL, only RL will be different. So only the last step would be different, where VTH divided by RTH plus RL. That means RL will be different, and you can find out the current. We can see these in the following examples. Okay, so here we have a problem to find the current through the 1 ohm resistor using Thevenin's theorem. So this is what we are going to be finding. This is our circuit, and the 1 ohm resistance is our load resistance. So according to Thevenin's theorem, I need to replace the remaining part of the circuit, which is towards the left of the terminals AB. The load terminals are AB, across which the resistance 1 ohm is connected. So I have to replace this with a Thevenin's resistance and Thevenin's voltage in series. So I have to find out VTH. Now how do I find VTH? First, remove the load resistance. Remove this by open circuiting. So just remove this load resistance, and you are going to find out the voltage across these terminals, which is nothing but the voltage across the 4 ohm, you can see, right? So now let's try to find out VTH. Just redraw the circuit. So where to find VTH, I'm going to be redrawing the circuit, which is the 12 volt in series with the 6 ohm resistance. Then I have the 2 ampere current. There is a 6 ohm resistance, and the remaining is the 4 ohm resistance. Now we have open circuited the load terminals, which is 1 ohm is removed. So these are the terminals A and B, right? So once we have this, so this is the voltage VTH we have to find out at the open circuited load terminals. So what is VTH? You can see it is the same as the voltage across the 4 ohm resistance. So to do this, let's observe the circuit. There is a voltage source in series with a resistance. So I'm going to be using source transformation to convert this. So there are different techniques to use. You can use any one of those. I'll be using source transformation now. So which means that I'll convert the voltage source 12 volt to a current source. 12 divided by 6 gives a 2 ampere, and the 6 ohm which is in series comes in parallel. So that is by source transformation. So using source transformation, this becomes 2 ampere and this becomes a 6 ohm resistance, and then another 2 ampere. This is the original 2 ampere, 6 ohm and the 4 ohm. So you can see that the 6 and 4 are in series actually now, right? And this is the voltage which we are going to be finding out. Now, since these two current sources are in parallel, so they can be added up together. So current sources in this which are in parallel can be added, as we know. So 2 plus 2 gives a 4 ampere, and 4 ampere current source in parallel to the 6 and this total 10 ohm resistance. So I'll again redraw the circuit like this. This will be 4 ampere, 6 ohm, and the total of 10 ohm resistance. So this 10 ohm resistance is going to be a combination of 6 and 4. Since this is open circuited, the 6 and 4 comes in series. So the same current will flow through both the resistances. So the current through the 4 ohm and the current through the 6 ohm is the same. So we are going to be considering it as a total resistance of 10 ohm. And now using current division, so this current will divide like this. So the total current through the 10 ohm resistance is going to be 4 into opposite resistance, which is 6 divided by the total resistance, which gives me a current of 3 by 2 ampere. Now this current is the same as current is flowing through the 6 ohm and the 4 ohm, that is the 10 ohm. So the same current flows. So the voltage across the 4 ohm, which is nothing but our VAB or VTH, is found out as VTH is equal to voltage is current into resistance. So current is 3 by 2 into the resistance, which is 4. So which gives you a 6 volt. So VTH has been found out as 6 volt. So first step is done. Now we go to the next step where you find out RTH. Okay. So for this, next step is to find out RTH. And to find out RTH, I have to remove the load resistance from the load terminals. I'll remove the 1 ohm resistance and find out the equivalent resistance at this terminals by making the sources equal to 0. So I have a voltage source and a current source. Voltage source will be short circuited, current source will be open circuited, and we'll redraw the circuit. So let's find out RTH here. To find RTH, so redrawing the circuit with all the voltage sources and current sources made equal to 0. So the 12 volt source is made a short circuit. So this, and the 2 ampere is a current source. So current source is open circuited. So that will also not be there. So now remaining is 6 ohm, and this is the 4 ohm, and these are the terminals. So across which we have to find out. So the effective resistance at the terminals AB, you can see that 6 and 6 are in series. The total resistance will be these two are in series, and this is in parallel to 4. So which means that your R equivalent or RTH is going to be equal to 12 parallel to 4, which gives you 12 into 4 divided by 16, which is a 3 ohm resistance. So which means that now the equivalent Thevenin's. So the last step is to draw the equivalent circuit, Thevenin circuit. So which gives you VTH and RTH. So VTH is how much? We got it as VTH is equal to 6 volt, and RTH we are having it as 3 ohm. And the load resistance. So load resistance is this resistance, which is 1 ohm, which we had open circuited. Now at the last step we'll be connecting it. So the load resistance RL is equal to 1 ohm. So what is the current through the load resistance? It will be 6 divided by 3 plus 1, which is 4, which is 3 by 2 ampere or 1.5 ampere. So this is the total current through this particular resistance using Thevenin's theorem. Okay. Now let's discuss what is called as the Norton's theorem. Like we said about the Thevenin's theorem reduces a circuit into a simple series equivalent, whereas a Norton's theorem is a simple parallel equivalent for a complex circuit. So coming to this, so how does it define? How is it defined? Any two terminals of a network can be replaced by an equivalent current source IN and an equivalent parallel resistance RN. RN value is the same as RTH. We'll see that. So this is a complex network with the load resistance connected. In the Thevenin's theorem, we were replacing this with a series circuit. Now here you can see there is a parallel circuit where there is a current source in parallel to a resistance. Current source is called as a Norton's current source. The resistance is called as Norton's resistance, and these are connected in parallel to the load resistance. So the load current can be found out as using current division. So current division says that this current will go through Rn and Rl. The current through the load resistance is found using current division as equal to IN into the opposite resistance, which is Rn, divided by the total value of resistance, Rn plus Rl. So this is how you can calculate the load current using the Norton's theorem, right? So now once we have done Norton's theorem, let's also find out how you find out the Norton's current. So now how do you find out the Norton's current? So you can see the complex network is replaced by the Norton's current source and the Norton's resistance. So when you're finding out the Norton's current, it's basically found out by short circuiting this load resistance. So the load resistance here is going to be short circuited instead of open circuited, as in the case of Thevenin's theorem. And then you find out the current through the short circuited load terminals. That is defined as the Norton's current. Now, what is Rn? Rn is the same as RTH, you can see. Why? Because you remove load resistance and find out the equivalent resistance by making all the sources equal to 0, which is the same as RTH. So you understand that Rn is the same as equal to RTH. And once you find out IN and Rn, connect up the circuit, find out the load current as we had seen before. Now let's do a problem with the Norton's Norton's theorem, you have to find out the current through the load resistance, which is given as, now here load resistance, load terminals are given, but for a value of 2 ohm, you have to find out the current through the load resistance is asked. So first, let us find out I Norton and Rn, right? So first, let us find out the Norton's resistance or Rn. So we know that Rn is the same as Rth. So to find Rn or Rth, both are the same, right? What do? We first make the load resistance. So here there's no load resistance anyway, right? So these are the load terminals, and here make all the sources equal to 0. So which means that I have to open circuit the current source, short circuit the voltage source, and I'm going to be redrawing it. So after short circuiting, open circuiting the 2 ampere source, I've got, I'm sorry. So after open circuiting the current source, 2 ampere part is gone. So I'm left with the 4 ohm resistance, and this is the 12 volt. Then there is this 8 ohm resistance, the 5 ohm resistance, and there is also another 8 ohm resistance here, and these are the terminals AB. So be careful while doing, find out. Remember that we have to find out the equivalent resistance at these points. So you can see that since the 2 ampere current source has been, this current source has been open circuited, so this 8 and 4 comes in series. 12 volt has also been short circuited. So effectively you can see that the 8, 4 and 8, these come in series. So 8 plus 4 is 12, 12 plus 8, 20. This 20 ohm comes in parallel to 5 ohm, and your equivalent resistance, you can find it out as equal to R equivalent or RTH will be 20 parallel to 5 ohm. 8 plus 4, 12. Yes, 12 plus 8, 20. So 20 into 5 divided by 25. So that is our equivalent R1, R2 divided by R1 plus R2. So this gives you, so this becomes 5, and you have an RTH of 4 ohm resistance. So RTH has been found out as 4 ohm. So now we have to find out the next step, the Norton's current. So Norton's current is found out by short circuiting these load terminals. So if I short circuit the load terminals, we can see that the 5 ohm gets short circuited. So the same current, Norton current, would flow through this short circuited terminal. So let me redraw the circuit and see how we are going to find out. Find IN short circuit terminal AB. Okay. So this makes the 5 ohm gets shorted, and hence we are ending up with the circuit, which is the 2 ampere current. Now I'm going to be converting this 12 volt voltage source in series with a resistance to a current source, because it's easier this way. So current source value will be equal to 12 by 4, which is a 3 ampere, and the resistance, this 4 ohm resistance, this one, which is in series with the 12 volts. So 4 ohm resistance comes in parallel, because we are doing source transformation to current. And then this is the 8 ohm, 5 ohm gets short circuited, and the remaining 8 ohm. This is the Norton's current. So we have to find out this current. So now we can see that there are two current sources. So I have converted this voltage source to the current source here. These two current sources are in parallel, so they'll give an effective of 5 ampere. So the 5 ampere current source now is in parallel to a 4 ohm resistance, and the remaining resistance, which is 8 plus, this is 8 ohm, and this is 8 ohm. And this is our Norton's current, right? So the 5 ampere current is going to come and split into this and this. So the total current IN will be can be calculated using current division again. So IN is equal to 5 into opposite resistance, which is 4, divided by the total resistance, which is equal to 20. So which gives you a 1 ampere. So I Norton has been calculated as 1 ampere. Now to draw the equivalent circuit, so which gives us I Norton, which is 1 ampere, current in parallel to the R Norton. R Norton we have calculated it as 4 ohm. This comes in parallel to the resistance. So in the problem, the resistance RL is asked to be 2 ohm. Find out the current through a load resistance of 2 ohm that was asked. So if there is a 2 ohm here, so what will be the load current now? This is your IL. So Norton's current is going to again split into this and this. So IL is found out as equal to IN into RN divided by RN plus RL, which gives you 1 into Rn is 4 ohm divided by the total resistance is 6, which gives you a 2 by 3 ampere. So this would be the current which is flowing through the 2 ohm resistance. So you can see that instead of 2 ohm resistance, if I replace it with a 5 ohm, IN and Rn remain the same. Only the last value which is obtained, Rn plus RL, only this has to be replaced. And Baki everything remains, the remaining are all the same. So you get a 2 by 3 ampere. So this is how we have calculated using the circuit using Norton's theorem. Okay. So seeing the relation between the Thevenin's and the Norton circuits, now we have the Thevenin circuit here, which is a VTH in series with an RTH. You have the Norton's source here, where Norton's circuit here, where Norton's current is parallel to RL and RL. So here we have a series circuit, here we have a parallel circuit. Now we know that if I do a source transformation on a voltage source, I get a current source. So if I do a source transformation on the Thevenin source, what will I get? Now the Thevenin's source, so the circuit, we have a circuit like this, which is your Thevenin's and RTH. If I convert this to and this is RL, and if I convert this to a current source, what do I get? Because I know that a voltage source in series with a resistance can be converted to a current source. So I'll get a circuit like this. So which implies that this current source should be equal to VTH divided by RTH, and the resistance will be equal to RTH. Now, if you compare these two, we know that Rn and RTH are the same. So if you're comparing these two circuits, uh, this one and this one, we can see that they are both exactly the same, which implies that IN should be equal to VTH divided by RTH. So we have here IN is equal to VTH by RTH, or in other words, I can find out the Thevenin's resistance as equal to Thevenin's resistance can be found out as equal to VTH divided by I Norton. So for finding out the Thevenin's resistance, another method is to find out Thevenin's voltage and divide it by the Norton's current, and you will get the Thevenin's resistance. So this method is what is used when you have dependent sources in the circuit. Why? Because Thevenin's resistance, to find out Thevenin's resistance, we normally make sources 0. But dependent sources cannot be made equal to 0. So in that case, we find out RTH using this method. Or one of the methods is finding out, one of the methods for finding RTH is to find out VTH, find out IN, and find out the ratio of those. That will give you RTH. Right? So now let's see. So the cases with dependent source, where, as I told you, RTH cannot be made, cannot be found if dependent sources are there. So dependent sources are, we are not able to make dependent sources equal to 0. So what do you do? RTH can be found out as, the first method is finding out VTH and IN and finding out RTH as equal to VTH divided by IN. This method we just discussed. Right? Now, there is another method in this case, that is if dependent sources are there, to find out RTH. That is my second method. This is like this. Like obviously turn off all the independent sources. Dependent sources cannot be made 0. Then apply an external voltage source VO at the terminals AB. So if you have a circuit, all the independent voltages are made equal to 0 here. And these are the load terminals. At the low terminals, you apply an external voltage, known voltage, which is VO. So VO could be any known voltage value, 1 volt, 5 volt, etc. Find out the current drawn by this circuit. Then VO. So since this circuit has all the independent sources made equal to 0, only voltage source is the voltage source which we have applied here. So obviously the resistance of this equivalent resistance should be equal to VO divided by IO. So this is your RTH. So this is a second method to find out RTH when there are dependent sources in the circuit, that you are going to be, instead of finding out I Norton, this is another method where we are actually making all independent sources equal to 0 and applying a known voltage source here, finding out the current by using any circuit analysis technique, and VO by IO would give you RTH. So this is the second method which we can use for finding out RTH. So depending upon whichever would be convenient, you use one of the methods to find out RTH when there are dependent sources. Fine. Now, so we have a problem here where we have to find out RTH and there is a dependent source in the circuit. Now to find out RTH when there is a dependent source, there are two methods which we already spoke about. First method is so we'll find it using both the methods and see. So method 1 is to find out RTH using VTH and I Norton. So VTH divided by I Norton. So I have to find out VTH also and I have to find out I Norton also. So to find VTH. So what is VTH now? We know that it is the open circuited voltage, which means this voltage here, it's open circuited already. So this voltage is VTH, which is also the same as Vx. So we can say that Vx is nothing but your VTH, right? So VTH is nothing but Vx. Now, observing this circuit, we can see that there is a 10 ampere in parallel to the 6 ohm. So if I do a source transformation, at this 10 ampere parallel to 6, I'll get a 60 volt in series. So 60 volt in series with the 6 ohm. This is the conversion of this 10 ampere source to converting this to voltage source, right? So 10 ampere current source is converted to voltage source here, and I'm getting here. So this makes the circuit a simple series circuit where this is Vx and this is nothing, the value is 2 ohm, and these are the terminals AB. So this is my voltage VTH, and we already know that VTH is Vx. So now this is open circuited, so there is no current flowing through this terminals, which means that this is a loop. So I'll write KVL and I find out that 60 minus 6i minus, okay, this value is 2Vx minus 2Vx minus Vx is equal to 0. Now, what is Vx here? Vx is the current through the 2 ohm resistor. So 60 minus 6i minus 3Vx is equal to 0. But at the same time, Vx we know that is equal to 2 into I. So substituting that, 60 minus 6i minus 6i is equal to 0, or I comes out to be 5 ampere. Now if I is 5 ampere, then Vx is 2 into 5, that is 10 volt, right? So I get Vx is equal to 10 volt by using this method. So this is the first part where I have found out VTH. Now the next part where I find out IN. Okay. So in this we have to so we have found out VTH already. Now we have to find out I Norton. Now I Norton is the short circuited current, which means if I short circuit this load terminals, the current flowing through this is Norton's current. So at the same time, we know if I short this out, the 2 ohm gets short circuited. So which means what? To find IN, I'm trying short circuiting. This is 6 ohm, this is 10 ampere, and that is my 2Vx. This is when I'm short circuiting, what happens? I'll just show it like this, and then I'm short circuiting this terminal. Right now, when I'm short circuiting this, what happens is that the 2 ohm also gets short circuited, or that gets shorted out, or effectively Vx becomes also equal to 0. Now, if Vx becomes equal to 0, 2Vx also becomes 0. Or I can redraw the circuit like this: 6 ohm, 10 ampere. Now there is no 2Vx becomes 0. If a voltage source becomes 0, it can be replaced by a short circuit. And this is our I naught. Now we can immediately see that since it's a short circuit here, the whole 10 ampere current will flow in this, which means what your IM is also equal to 10 ampere. I hope you understood. The when I'm shorting this terminal out, uh, this terminal, when it is shorted out, it is shorting out the 2 ohm. Now 2 ohm Vx is the voltage across 2 ohm, right? So Vx also becomes equal to 0 since it is shorted. Vx becomes equal to 0, and once Vx is 0, 2Vx also becomes 0. So that is also replaced by a short circuit. So now I'm replacing this. So since this is all short circuit, obviously the current 10 ampere is not going to flow into the 6 ohm. It will flow through the short circuit, which means IN is basically equal to 10 ampere only. So what have we got? We have to find out RTH. So RTH is equal to VTH divided by I Norton, and VTH is equal to 10 volt. IN is 10. So we have RTH as equal to 1 ohm. So this is how we find out RTH, by finding out both VTH and I Norton. Now the same problem if I do it with method 2. Now method 2 says that in here I will apply an external voltage source and find out the current. Or I apply an external current source and find out the voltage. Okay, that is another method. That is instead of, like we said earlier, so the circuit here we are going to be applying a known voltage source and find out the current IO. VO by IO will give you the resistance, or you can also apply a known current source. That is also possible. So IO, and obviously the voltage across this, which is VO. Again, VO by IO, RTH is nothing but equal to VO divided by IO. So this method is what we are going to be using here. So now let's see. There is also, remember that when we are seeing all independent sources 0. Here also independent sources are 0. So here for this is the circuit which we are saying. So for this any circuit. So in this case our circuit is this one. This circuit is what we have, and I'm going to be applying a current source instead of a voltage source. I'll apply a current source. You can apply any one of those. Now at the same time I have to take out this because it's an independent source. So independent source has to be made 0. Current source is open circuited. So once we do that, what do we do? So make the 10 ampere source 0, that is open circuit. So I have open circuited this, the 10 ampere source, and what we are having is remaining, there is this 6 ohm. Now the 10 ampere is open circuited, so I will be left with the plus or minus 2Vx source and this 2 ohm. So that is our Vx. Now I am going to be applying an external source. So at this terminal, so what we said is at this terminal you apply either a known voltage source or a known current source. Both of that can be done. So here so that I can apply KCL, current source would be easier. So I'm just applying a 1 ampere source over here and finding out the voltage. The 1 ampere and the voltage across it is obviously Vx only. So if I apply node analysis, what do I get? If I apply node analysis at this terminal, I get Vx divided by 2 plus Vx plus 2Vx divided by 6. Why is it so? The current through the 6 ohm. So I'm applying node analysis at this point. Current through the 2 ohm resistor is Vx by 2. Current through the 6 ohm resistor is Vx plus 2Vx divided by 6. So I'm going like this, Vx minus 2 plus is plus. So Vx plus 2Vx divided by 6. These are the currents which are leaving the node, and the current which is entering the node is equal to 1 ampere. So which means when I'm solving this, I'll get Vx for, so Vx plus by 2 plus 3Vx by 6 is equal to 1. And if you solve this, you get Vx is equal to 1 volt, right? So Vx is 1 and the current is 1 ampere. So what is RTH? RTH is going to be equal to 1 volt divided by 1 ampere, which is 1 ohm. So this is the same answer which we got in the last slide, where we saw that we found out RTH using VTH divided by I Norton. So here we are using this method, and we can see that in this method, this method is easier because we do not have to, I mean, in the other case, we had to find out two parameters, one VTH, the other one I Norton, applying both the different conditions. But here we are just applying an external voltage source, or here I have applied an external current source. Find out the voltage across it. In this case, the voltage across it, it is the same as Vx, or the what do you say? We can say that this is the Vx is the node voltage at this point. The voltage across the 1 ampere source is nothing but the voltage across the 2 ohm, and that is Vx, right? So applying node analysis, you can very easily find out the value of Vx. And once I have found out Vx, the current is already known. So the voltage V divided by the current will give you RTH. So what that is done, and we're getting the same answer, right? So any one of these methods can be used depending upon whichever is easier. So these are the two methods to find out RTH when we have dependent sources. Like we discussed before, dependent sources cannot be made zero to find out RTH. Only the independent sources can be made zero. So you have to use one of these techniques to find out RTH. Okay. So now in summary, we have discussed about the Thevenin's and the Norton's theorem, and both are very useful theorems which can be used to solve complex circuits. Here they replace this is done by replacing whatever complex circuit is with a simple circuit. It's a series circuit for the Thevenin's case, or a parallel circuit if it is a case of a Norton's theorem. So both the cases with independent and dependent sources with examples have been discussed. So basically, these are very useful when we have circuits with variable loads, like we had seen for the in the examples. If I am to find out suppose I want to find out the current using Norton's the Thevenin's theorem. So IL is given by VTH divided by RTH plus RL. So for just if the only the load is varied, only the load is going to be varied, VTH and RTH remaining the same for the circuit, we have to find out VTH and RTH. So once we find out VTH and RTH, this procedure need not be repeated, and you have to just replace it with the load resistance. So for variable loads, this theorem becomes very easy to use, or very handy. Similarly, this is for Thevenin's, and the case with Norton's is you find it out as IN into Rn divided by Rn plus RL. Here also you can see that IN and Rn, once we find it out, you need to only replace RL here. So for variable loads, you can use, so whenever circuits with variable loads are there, you can use the Norton's theorem or the Thevenin's theorem, depending upon whichever is the case. So sometimes if it is a parallel kind of circuit, then we would prefer a Norton's circuit because it has a current source. And if it is has voltage sources and forming loops or meshes, then we would prefer a Thevenin's theorem where a series equivalent circuit is formed. So this is all about Thevenin's theorem and Norton's theorem, and how to solve circuits using the Thevenin's equivalent and the Norton's equivalent. Thank you.